So this is a short video on alkanes. Alkanes are an example, or the first example you meet on the GCSE course of a homologous series. So before we go any further with our look at alkanes, we need to look at exactly what a homologous series is. And it immediately becomes apparent that I've got the wrong function on the board. So what exactly is a homologous series? So as it says here, there are three key properties that you need to know about a homologous series. They have the same general formula, they have the same chemical properties, and they have gradually changing physical properties, which depends on the size of the molecule. Now, you need to know all three properties of a homologous series. When talking about them with my classes, I generally refer to them being like my family. My family, as you can see, the three males here, we do all look very similar. So the Roberts family, we look similar because we have very similar DNA. Okay, now how does that apply to alkanes? Okay, well, alkanes all have the same general formula. So any chemical which is CnH2n plus 2 belongs to the alkane family of hydrocarbons. So in other words, if you've got hydrogen ratio which is double plus 2 the number of carbons. Same chemical properties. Well, the Roberts family, we're all big Tranmere Rovers fans, so we all react in the same way when Tranmere Rovers score. Likewise, we react with despair when Man United score. We're not big fans of Man United, so we all react in the same way. Likewise, alkanes all react in the same way. So we would say that we all have the same chemical properties. And for physical properties, well, you can see that the three males of the family, two brothers and a dad, we have very similar physical properties. We're all quite tall, we're all quite streamlined, but we have slightly different physical properties. You see this gentleman here, okay, is slightly taller than this gentleman here, and this gentleman here is the shortest. And so unsurprisingly, this person here is the strongest, and this person here at the end is the least strong. And the alkanes are the same. Their physical properties, whether they boil or melt, the point at which they do these depends on the size of the molecule. Okay, so that relates the physical properties of our compounds to the size of our compounds. Let's move it away from that fairly gory family shot and onto the alkanes themselves. So we describe them as saturated hydrocarbons. So we need to define the term saturated first. Okay, and saturated in organic chemistry means that the compound only contains single covalent bonds. Alright, and our second definition, which we need to cover, is about hydrocarbons. So a hydrocarbon is a compound which contains carbon and hydrogen, and the key word at this point is only. They only contain carbon and hydrogen. Nothing else. They don't contain oxygen, nitrogen. Alkanes, or sorry, hydrocarbons only contain carbon and hydrogen atoms. And alkanes all have the same general formula. So here's our general formula here. I've just scrubbed it out. Okay, they all have the same general formula, CnH2n plus 2. And you'll see that applied down here. I'll get rid of that yellow pen. I don't think much of that. So methane, 1 carbon, 4 hydrogens. So we have 1 carbon here. Now if you look at your periodic table, you'll see that carbon is in group 4. That tells you it's got 4 electrons in its outer shell. It needs 4 more electrons in order to complete its outer shell. So carbon forms 4 covalent bonds, and those 4 bonds go to hydrogen. Okay, hydrogen only forms 1 covalent bond because hydrogen only has 1 electron in its outer shell, and in that inner shell it only needs 2 electrons to be full. So there's methane, the gas which comes out of gas taps and comes out of your kitchen hob. We'll move on to ethane. Ethane is the next molecule in the alkane homologous series. So we started with 1 carbon, now we'll have 2 carbons bonded together. And to finish off ethane, we'll have a look at this carbon here. We've already made 1 bond, so 1, 2, 3, 4 bonds. This carbon here, 1, 2, 3, 4 bonds. And on those spaces, we put hydrogen. And counting up, we can see that our molecular formula of ethane is C2H6. Propane is the next one in the series. It's going to have 3 carbons. I'll just draw it, running out of space a little bit. I'm going to draw it over here. There's my 3 carbons. This carbon here has already formed 1 bond, so we need 3 bonds there. H, H, H. This carbon in the middle has already formed 2, so it just needs 2 more bonds, and on those we put hydrogens. And the carbon at the end, well, it's got 1 bond down here. Hydrogen, hydrogen, hydrogen. And if we count up 1, 2, 3 carbons, we then count up our hydrogens. Working our way round, we can see that propane is C3H8. Now hopefully you can spot the pattern emerging, that the DNA, if you like, the general formula, CnH2n plus 2, works for all these molecules. If you had 1 carbon, double it to make 2, add 2, gets 4. If you had 2 carbons, double it to make 4, add 2, makes 6. 3 carbons, double it to make 6, add 2, gives you 8. So you can see that our general formula does work. So therefore, if you have butane, that will be C4. How many hydrogens are you going to have? Well, again, back to your formula up here. Double the number plus 2. So 4 times 2 is 8, plus 2, 10. So butane, C4H10. And pentane, well, pent suggests you've got 5. C5H, well, double 5 gets 10, plus 2, that gives 12. And we could draw butane out if you like, or we could draw pentane out. But let's draw butane. So we've got 4 carbons. Put your bonds on. So this one has already got 1 bond, so you have 3. This one here has got 2, so you put 2. This one's already got 2. 2 more. This one on the end. 1, 2, 3. Every carbon there has therefore got 4 bonds. You fill up the bonds with hydrogens. Hopefully you're going to be a bit neater than I am. Still not quite used to using this board. And that gives you your lovely, what we describe in chemistry as a displayed formula of butane. So you can see 4 carbons surrounded by your 10 hydrogens. Naming is critical, and you need to remember a way of remembering that meth only contains 1 carbon, eth always contains 2, prop contains 3, and bute contains 4. Once we get past bute, we move on to a much easier system of naming, where the prefix represents the number of carbons, like they would do with shapes. So pent has 5, hex has 6, hept has 7, oct has 8, and so forth. So the phrase that I always remember is that meerkats enjoy proper banter. So meerkats enjoy proper banter. And that helps you to remember how you name your alkanes. Now, sometimes our alkanes don't form in a straight line. Now, hopefully you'll remember that butane, meerkats enjoy proper banter, has 4 carbons. C4H, well, 2 times 4 is 8, plus 2, 10. So C4H10. And we drew it on the first page and we had a lovely straight line of those carbons. That's what we drew on the first page. But the definition, and I'm sorry I'm writing over it, of isomerism is that things can have the same molecular formula but a different structural formula. So rather than me drawing the carbon chain in a straight line, what I could try and do is form the carbon chain with what I would call a junction in it. So here's 3 carbons, and then rather than having a curve at the end, that would effectively give the same thing, I put a T-junction in it. Again, I then need to put my hydrogens on, and so this carbon here, 1, 2, 3. This carbon here has now got 3 bonds, so 1 hydrogen, this carbon here, 1, 2, 3. This carbon on the end, 1, 2, 3. And put my hydrogens on, because if it's going to be an isomer of butane, it needs to have the same molecular formula. So we need to count up to check that we've got the same number of hydrogens. Well, here I've got 3, 4, 5, 6, 7, 8, 9, 10. It works, C4H10. But that's clearly a different structure. You've got a junction in it. What you do find some pupils doing, or other people, is trying to put the carbon, actually that would just give the same thing, trying to put that on as a curve at the end. Now actually that arrangement is effectively a straight line. It doesn't matter whether the carbon which is bonded on here is drawn up there, that's still a straight chain of carbons effectively. What's different about this one is it has a junction in it, okay, a T-junction, so that's no longer a straight chain of carbons. And what you should be able to do is then apply this to pentane. Okay, so pentane has 5 carbons. You can then see about working in a T-junction onto pentane. Now I'm going to move forward because I want to look very quickly at 2 reactions of alkanes. And the first one is combustion. So let's imagine we take methane. I just need to swap my pen over. Methane burns very, very willingly. Okay, it combusts, and combusts means it reacts with oxygen, and hopefully you should know that when you combine a hydrocarbon with oxygen, provided there's enough oxygen, you combine the carbon with the oxygen to give carbon dioxide, and the hydrogen combines with the oxygen to give water. And you obviously need to balance that, so we've got 4 hydrogens, 2 over here, so we'll put a 2 over there. Now we've got 4 oxygens on the right, only 2 there, so we need to double that. Now that only works if you've got sufficient oxygen in there. If you've not got sufficient oxygen in there, worryingly, you produce CO, okay, and that's from incomplete combustion. Okay, now that's if there's not enough oxygen in there. And the problem with CO, which you definitely need to know for the exam, is that point 1, it is toxic. Okay, you always get a mark for just writing toxic. And the reason it's toxic is it binds irreversibly to hemoglobin. So it effectively stops the hemoglobin from transporting the oxygen around the body. So you effectively suffocate. The second reaction which you need to know on the IGCSE syllabus is the halogenation of alkanes. Now that only happens in the light, because what happens is you need UV light in order for the reaction to occur. So let's draw the reaction with bromine in UV, and what happens is you swap one of the hydrogens for one of the bromines. It's a substitution reaction. So here is our product. We keep all of the hydrogens apart from one and replace that with a bromine. And obviously this bromine here is swapped with the hydrogen, so the other product is hydrogen bromide. Now that reaction also works with chlorine in exactly the same way, and it's important that you note that it's a substitution reaction and that UV light has been used. And that's the end of this clip.